We have here three functions, and we have to discuss the convexity of these functions. And for that, we need to analyze what is the sign of the second derivative, right? So let's do that one by one. So let's begin with the first. We take first the first derivative, okay? But one way to write this is we can split this as um, x to 1 plus 2/3 is equal to 5/3 minus 2 times x to 2/3, right? And then if we take the derivative of this expression, then this is equal to 5/3 x to 5/3 is 2/3, right? Minus 4/3 times x to the minus 1/3, right? So this derivative exists in r minus 0. So the function is defined everywhere in r, right? Because you can evaluate the function everywhere. However, you can't evaluate the derivative at 0 because the derivative diverges, right? Okay, you see the plus or minus infinity when your x goes to 0 because of this term here. This does not have any problem. The limit of this is 0, but this one does because there's a singularity. Now we take the second derivative here, and what we have is 2/3. So you multiply this by 2/3, so that's 10 over 9, right? And then x to minus 1/3 minus, and then with the minus is a plus, and then you have 4 divided by 9, x to the power minus 4/3. All right, this minus 1/3 minus 1, minus 4/3. We're going to take out common factors. So for instance, you have a factor 2 over 9 that is common in both coefficients. So 2 over 9, and then we're going to take this as a common factor. It's a global factor, right? So what we have here is 5, okay? And here we have just x, right? Because if you multiply x by this, you get x to minus 1/3, right? And here you have 2. Well, as a matter of fact, we can factor out the 5 too, right? So let's do that. We factor out the 5, and instead of these 2, we have 10, right? And then what we have here is just x plus 2 over 5, which is more clear, right? This is more clear expression of what you get at the end. Okay? Now it's a matter of analyzing this. But this term is no problem because actually this is 1 over the cubic root of x4. Whatever the sign of x, whatever the sign of x, x4 is always positive, so this number is always positive. Of course, it is not defined as 0 because the derivative is not defined at 0 either, right? So clearly the second derivative cannot be defined at 0. But anywhere else, this factor is always positive. So the sign depends on only this, right? And this sign is negative. So if x is smaller than minus 2 over 5, this sign is negative, so f second is negative. And if x is larger than minus 2 over 5, then f second is positive, right? So this means that the function is up to minus 2/5 is this is concave, right? Concave. And beyond this point is convex, right? It's always convex. All right. At that point, so this point here is an inflection point because the concavity of the function changes, right? At precisely that point. All right. Well, if you want to know what this function looked like, this function is always negative, right? For x smaller than 2 is negative, for x larger than 2 is positive. Diverges, the derivative diverges at 0. At 0, the function is 0. So it looks something sort of this. here, if this is the point minus 2/5, what you have here is the slope here is infinite, right? Because the derivative is infinite. And then it goes like this, and it goes like this. I'm exaggerating, right? But this is what it looks like. So here you have an inflection point at that point. So it's convex here and concave here. From this point, well, from this point on, it's always convex. So what you have here is something like this, right? It goes through this point too, and it goes like this. Well, you know what I mean, right? It goes like a parabolic branch of this sort, right? Something like this. Okay, and there is a minimum here. We haven't worried about the minimum. The minimum would be the solution of f prime equal to 0. Well, you can calculate if you want. I think it should be something like 4/5. Not completely sure, but I think it's 4/5. But it doesn't matter because we're not concerned about that. Our concern here is what is the concavity of the function, and the concavity is described that way. All right. Okay, let's go to the second function. Okay, the second function has a similar problem, right? Because of the way it's defined in terms of absolute values. This function is positive or negative? Yeah, positive. So in terms of absolute values, this function is not differentiable at the point 0, right? Okay, so on the other hand, there is a symmetry, an obvious symmetry, because given that it is defined in terms of absolute values, if you change x by minus x, you get the same function. So what I'm going to do is I'm going to plot this function, well, at least to analyze this function in x larger than or equal to 0, right? And that tells us everything. Well, by the way, not larger than or equal to 0, because as I said, well, the derivative is not a differentiable function, so it's not going to be, this function is not going to be differentiable at 0, right? Okay, so what you have is, for this region, the function looks like this, and then you can take the derivative, and that is equal to 1 times the exponential plus x times the derivative of the exponential. So 1 plus x times the exponential. Okay, that's the first derivative on the positive side. Okay, then on the positive side again, if we take the second derivative, so the derivative of that expression here, what you get is the derivative of this, which is 1, so the exponential, plus this times the derivative of the exponential, which is the exponential itself. So what you have is 2 plus x into the x. And now we need to analyze the sign of this. This factor here is positive because it's an exponential. Exponentials are always positive, right? So everything, well, the sign depends on this factor here, right? So this factor is well, it's actually for x positive. Remember, x is positive. This is also positive, right? Because x positive plus 2 is a positive number, so this is always positive. So that means that the function f is always convex in x positive and in x negative, right? Because as I said, the function is even, which means that it's symmetric with respect to the vertical axis, right? So if it is convex in one side, it's also convex in the other side. So it's convex everywhere, but the only peculiarity of this function is that it doesn't have a well-defined derivative at the point 0, okay? If you question or if you wonder what this function look like, it's pretty much something like this. It goes like this, so the branch is exponential, but it's got a cusp here, so it goes like this, okay? So you see it's convex, okay? But here, the slope here is -1 and the slope here is +1, right? So like this. because we have an absolute value, and this is a point where the function is not differentiable. All right. Then we have this third function, right? It's the logarithm of a quadratic polynomial, which is x squared minus 6x plus 8. X squared is equal to logarithm of x squared minus 6x plus 8, right? So actually you can rewrite this as the logarithm of two factors, which are x minus 2 and x minus 4, right? Because then the sum of the two roots is 6 and the product is 8, as we have here, okay? So this is what we have, right? Which, by the way, tells us where this function is defined. This function is defined only outside the two roots, right? So for x smaller than 2 and or x larger than 4 is defined in this region. So in the interval minus infinity 2, 4, infinity, right? Between 2 and 4 the function is negative, right? Because this is a parabola, right? It looks like this. Okay, this is the point 2, this is the point 4. So it's not well defined here because the argument is negative, right? The product of the parabola is negative, okay? And it is well defined here and there. And of course, at these 2 points is 0, and the logarithm is not defined either. So we have a function that is defined in two discontinuous regions, okay? For x larger than 4 and for x smaller than 2. All right? So now we have to analyze the what is the derivative of this function, okay? So we can do this using the knowledge we have of this, right? So what we're going to do is to let me think a little bit. Okay, well, actually, I think it's better to take the derivative here. So f prime here is equal to, the derivative of this is just 2x plus 6, sorry, minus 6, 2x minus 6. And this is, well, we can write down the denominator as x minus 2, x minus 4 if we like to, or just as x squared minus 6x plus 8, but better suits us. As a matter of fact, there is a global factor 2 here, and the factor we have up here is x minus 3, right? Then we have to take the second derivative of this, okay? So the second derivative is equal to, there's a global factor 2, and then we have the derivative of this, which is 1 multiplied by that, which is x squared minus 6x plus 8. And then we have to subtract this factor x minus 3 by the derivative of this one, which is this one, so is therefore twice this factor. And in the denominator we have the square of the denominator, which is x minus 2 squared, x minus 4 squared here, right? Okay. We can simplify this expression, right? So the global factor 2 here, and then you have x minus 2 squared, x minus 4 squared, and this one here is equal to x squared minus 6x plus 8 minus 2x squared plus 6 times 2 is 12 plus 12x is twice this and this, so 6 multiplied by 2 is 12, right? And then minus 2 times the square of this, which is 9, so it's 18, right? So we have that. And if we simplify that expression, we again have this factor here, x minus 4 squared. What we have is x squared here, and minus 2x squared is minus x squared, right? Then you have minus 6x plus 12, so this is plus 6x. And then we have 8 here, minus 18, which is minus 10, all right? And this is equal to minus, let's take a global minus here, so we have minus 2 over x minus 2 square, x minus 4 square, and then this quadratic factor, which is x squared minus 6x plus 10, right? Okay, 6 squared is 36, so 6 squared minus 4 times 10 is 36 minus 40, which is negative. So the discriminant is negative, so this is an irreducible quadratic factor. The coefficient of the x squared is positive, which means that the whole factor is positive because it never crosses the axis, right? So we have here a positive factor. Also here we have a positive factor because it's the product of two squares, right? So because of the negative factor that we have here, the global sign of this second derivative is negative, okay? Which means that the function is concave. So f is concave in its domain, which is, as let me remind you, it's just this couple of intervals, discontinuous intervals that we have there. So this function is discontinuous and pretty much looks like something like this. So you have here 2, here you have 4. Well, it will look something like this. This is these are asymptotes, so it's going to be something of this sort. Concave here, concave there. All right.